Well, thank you so much for that kind introduction, and thank you to the organizers for organizing such a nice workshop. I'm really happy and honored to be a part of it. Today I'll be talking about non-backtracking eigenvector methods for hypergraph community detection. I'm going to kind of start out with a broad overview of all of the background information we would need to understand kind of each of the words in this title. So don't worry if that title sounds a little dense. We'll get there. The work that I'll be presenting today is joint work with a couple of exceptional collaborators, Phil Chodrow, who is at UCLA, and Nicole Eichmeyer, who is in computer science at Grinnell. So let me run through briefly just an outline of what I'll be talking about today. So I'll begin with defining some background information and kind of reminding a lot of us of some of the techniques for community detection for graphs before moving on to hypergraph data and focusing on the non-backtracking operator, which I'll define, and proposing some eigenvector methods for hypergraphs on this using this non-backtracking operator. And then finally, I'll end with some comments on detectability thresholds, and I'll point to some challenging open questions, but I think very interesting ones, and ones for which we have some preliminary evidence. Okay, so I'll begin, as I said, with background, some background information and a reminder about approaches for graph community detection. All right, so I'm sure we don't need the slide, or maybe have already seen the slide this morning, but let me just remind you, a graph consists of a set of nodes and a set of edges. Each edge in a graph is a set of two nodes, right? We have the connection between two nodes. This is in contrast to hypergraphs, which are built very similarly. We still have this same kind of concept of a node set, but the edges now in the edge set for a hypergraph can contain any number of nodes. So in this picture, I have visualized some kind of regular graph edges, which are collections of two nodes, but then there are also these collections of what we call three edges. So edges that connect three nodes together. Okay. And I should say, feel free to interrupt me with any questions. So you can raise your hand or drop them into the chat. Either one will suffice. Okay, so we've got one of the words in the title knocked out, it's defined. So where does, why do we consider hypergraphs? Where do hypergraphs data arise? So there's a lot of really natural ways to model real world data with hypergraphs. So for example, if you have data representing interaction, for example, here, or I guess not an example, but to say more about what I mean, here the nodes could be agents and the edges could represent events in which the agents interact. So this could represent, socializing in groups, attending events. I have to apologize, I'm a huge Office fan, so you'll see throughout the talk a few images from The Office. So for example, here we have the agents, the nodes here are the characters of The Office, and they're interacting in this image in a Christmas party event. Okay, we could have collaboration. So the nodes here could be potential collaborators, and the edges are the projects or teams in which those collaborators collaborate. So this could represent, for example, scholarly papers in which there are multiple co-authors, legislation in which members of Congress or other political or government bodies are co-writing pieces of legislation, etc. Okay, and then finally, this data arises in representing the concept of co-presence. So for example, the nodes could be ingredients and the edges could be recipes formed from those ingredients. And if you're, I feel like I have to explain this picture because if you're not an Office fan, you maybe are wondering what's going on here. So this is someone who's carrying a big vat of chili in which, of course, numerous ingredients have been combined to form Kevin's famous chili. All right, so hypergraph data, as we can see, is quite natural. And so let's talk a little bit about what the hypergraph community detection problem, which is really the focus of what our approaches are for in today's talk. So let's talk about what this is. So given some hypergraph data, the goal of the hypergraph community detection problem is to assign each node to a community or cluster of related nodes. Okay, and in kind of the stereotypical interpretation of community detection, related often means densely interconnected. We want to understand what subsets of nodes are densely interconnected when related, when compared to the connections between clusters. Those should be relatively sparse. And there are applications here in social network analysis for learning kind of subgroups of social interacting agents, drug discovery, image processing, data visualization. I'm sure many people here could contribute to this list and point to their favorite applications. Okay, a super brief reminder, in case it's been a long time since you've taken linear algebra. A vector is an eigenvector of a square matrix with a given scalar eigenvalue lambda if this vector satisfies this matrix vector equation. So A, the matrix A times the eigenvector should produce just a scaling of that vector with the scaling parameter lambda. Okay, and then finally, my last bit of background definition, just a reminder that when we have a graph, there are many ways of representing a graph in matrix form. Perhaps, or almost surely, the most popular and the most widely known is as its representation via the adjacency matrix. Okay, so if this is our graph over here on these 5 nodes with 5 edges, then the adjacency matrix has entries which are indexed by pairs of nodes. Okay, so you can think of all of the rows and columns, each correspond to a given node. Maybe we have A, B, C, D, E, and A, B, C, D, E. And the entries of the adjacency matrix represent whether there is an edge existing in the graph between the 2 corresponding nodes, right? So here, this kind of upper 1 and this one both represent the edge connecting nodes A and B. All right, so let me briefly remind you of some approaches from graph community detection. So first of all, let's talk about why we model graphs with communities. So suppose we have these n nodes and we divide them into 2 groups, A and B. And for each pair of nodes, I and J, we're going to draw an edge. We're going to randomly sample and introduce an edge in the graph with probability Pij. Here, I and J, again, are indexing the nodes. And we're going to imagine that because these nodes were divided into 2 groups, A and B, that there's going to be 2 probabilities that Pij can take on. There's probability P, and that is the probability of sampling if I and J are in the same group. And then there's probability Q if I and J are in different groups. Okay, so what this gives us is an adjacency matrix, right? We've sampled a graph structure. Graph structures are bijective with adjacency matrix, but this adjacency matrix has noisy block structure, right? The blocks here are represented by the fact that we sampled with 1 probability in the same group and with a different probability outside of that group. So there is some block structure in this matrix, but it's noisy because we were only sampling with these probabilities. Of course, some of these are missing. So this structure that we've built is called a stochastic block model. And what you can see is that if we think about the probability matrix, so this is the matrix that just represents with which probability we were sampling for each pair of nodes. A looks a lot like that matrix, just with some noisy structure. Okay, so you can compute the leading eigenpairs, so the largest magnitude eigenvalue and corresponding eigenvector, and the same for the second largest eigenvalue. And what you find is that associated to the largest eigenvalue, there is this constant all ones eigenvector. So this isn't a very useful eigenvector. Looking at it doesn't tell us anything distinctive about the nodes. However, in the eigenvalue associated to the second largest eigenvalue, we end up with this very clear view of the block structure. So again, sorry, I should say this is the eigenpairs of our probability matrix P. And so what we can see is that the nodes associated to each group are distinguished by the sign of their corresponding entry in this second eigenvector V2. Okay. And so, we don't know when we're just faced with one of these sampled graphs, we don't know this underlying matrix P. So the hope is that we'd be able to learn from that noisy structure that we do have access to, this very clear community structure. And the good news is that it's a fact from random matrix theory that eigenpairs of A are close to those of P with high probability as the number of nodes N grows large. Okay. So what this leads us to is an algorithm for graph community detection. So the steps here are fairly simple and straightforward. We're going to compute the second largest eigenvector of the adjacency matrix A. And then we simply look at the sign of the entries. If the sign of the entry in V2 corresponding to node I is positive, we're going to guess that that node is in group A, and otherwise we're going to guess that it's in group B. So for this noisy sampling from our probability matrix, we end up with this vector, and you can see that the community structure is almost entirely recovered. There's this one kind of misclassified node. All right, and like I said, let me know if there are questions. All right, so that's all of the background material for the talk. And so now I'm going to jump into things that are maybe familiar to some, but likely a little bit less familiar. And so I'll go into more detail. So I'm going to focus today's talk on the non-backtracking operator, and I'm going to show you how to develop eigenvector methods for non-uniform hypergraphs using that matrix. Okay, so first of all, matrices for hypergraphs. What do we mean by that? So we have a few options here. One way of trying to encode the edge structure of the hypergraph is to transform the hypergraph into a graph and then use the well-studied techniques for matrix representation of graphs on that projected graph. Okay. Now, one issue with that is that that loses multi-way information. So if a clique of two edges in your graph is truly different, truly has a different meaning than a three hyperedge, a three edge in your hypergraph, then you've lost that information. Okay. So we'll set that approach aside. That is something you'll see we compare to later on. But another approach is that rather than trying to use only matrix information to represent our hypergraph, we could instead use tensor, higher order matrix representations of the adjacency structure. So we could have a 2 tensor associated to 2 edges, a 3 tensor associated to 3 edges, a 4 tensor associated to 4 edges, and so on and so forth. So here, if we think about the 3 tensor, right, this is indexed by 3 indices ij and k, which are going to represent the ij and kth nodes in our graph. And we'll simply place a 1 in that entry of our kind of rectangular solid tensor if the edge on ijk is realized in the graph and a 0 otherwise. Okay, but again, immediately trying to generalize the previous techniques that we saw for graph community detection is problematic because we know how to calculate eigenvectors of individual tensors, but trying to calculate eigenvectors of sets of tensors, especially tensors of different order, is not well understood yet. Okay, so what should we do? So the approach we'll take is actually to generalize, and I shouldn't say this isn't our approach, but one of the approaches in the literature is to generalize what's known as the non-backtracking operator to hypergraphs. So the adjacency matrix, as a reminder, is n by n. It's indexed nodes by nodes. Meanwhile, the non-backtracking operator, which we'll denote B, is a matrix that operates on edge node pairs. So it's indexed by a pairing of both an edge and a node. So to introduce this matrix, let me first define a relation, which I'll refer to as points to. So the pairing edge 1 and node V1 points to edge 2 and node V2 if V1 is in edge 1, V2 is in edge 2, V1 is in edge 2 and is not equal to V2, and those two edges are not entirely equal. They don't correspond. Okay, so the way to think about this, this relation, this points to relation, is that you can get, so here's an example, I can get to V2 in edge 2 from edge 1 by passing through V1. I can get to V3 in edge 3 from edge 2 by passing through V2. So you can see that these edges are never the same. The nodes that we pass to are never the same, but this is giving us a walk structure through our hypergraph. Okay, and so once you have this kind of relation understood, then defining our non-backtracking operator is fairly simple. We're simply going to take a matrix, which, like I said, is indexed by node edge pairs, and we're going to place a 1 if the row indexed edge node pair points to the column indexed edge node pair, and a 0 otherwise. All right. So this was popularized for graphs by Hashimoto in 1990. And then it was a couple of years later, there was an important theorem by Bass, and I think generalized also by another author, which I'm forgetting. But this gives it kind of a more efficient computation, and we'll see some examples of this in a moment. It was formulated for hypergraphs by Storm in 2006, and then rediscovered for hypergraphs in the context of community detection by Angelini et al. In 2015. And the non-backtracking operator has been considered in a lot of very interesting places. It has a lot of really cool topological connections. So if you're interested in prime cycles or zeta functions, I encourage you to look into the non-backtracking operator. Although we're really considering a data scientific problem here, we want to find the community detection using, or find community structure in our hypergraphs using this operator. Okay, and a couple of the things I want to highlight is that we can represent hyperedges of all sizes in the same matrix here, right? So if we just take all of the edges in the hypergraph and all of the edge node pairings, and we give every one of those its own entry in an index in both the row and column of our matrix, then we automatically get this representation of all of the hyperedges, right? There's no problem here of needing, you know, data representation of different orders. It's all just present in this matrix. And in our stochastic block model from before for the graphs, it's known that the eigenvector associated to this second eigenvalue is correlated with the community structure if that eigenvalue is real value. Okay, and so the picture is something like this. If we were to plot the spectrum of our non-backtracking operator, then our second eigenvalue, if it's real, lying on the real line, when we take the eigenvector, the second eigenvector, and we aggregate the information about entries corresponding to the individual nodes, then we get this noisy representation of the community structure, right? So here's the true partition. All of these nodes are of one community. All of these nodes are of another. And you can see that we would be off only on very few nodes. We would have misclassified very few nodes. All right, but issue number one, computation. So as I said before, when we have the adjacency matrix, it's very neatly always number of nodes by number of nodes. In contrast, the non-backtracking operator is indexed by edge node pairs. So that means that our non-backtracking operator is of size m, I'm just going to call this k for now, mk by mk, where m is the number of edges and k is the average edge size, right? So this can grow very quickly. For example, a small data set might have 300 nodes, 8,000 edges, which with each of those 8,000 edges on average representing 2.5 nodes. In that case, this single dimension of our non-backtracking operator is about 20,000. So it's already quite a large matrix. And to do eigenpair computations on a matrix of that size gets expensive quite quickly. Okay. So one of the first results that I'm going to present today is a generalized Ihara-Bass theorem. Okay. So under mild conditions, if we have an eigenvalue of the non-backtracking matrix, then one of two things happens. Either that eigenvalue is real valued and lands in this kind of uninteresting pile of values, 1, -1, -2, all the way down to 1 minus k bar, where k bar is the number of distinct edge sizes. And this is associated with no structural information about the hypergraph. Or, and this is the interesting case, this eigenvalue is also an eigenvalue of a much smaller matrix, which we're going to call B prime. Okay, so here B prime is of size 2 k bar n by 2 k bar n. K bar, like I said, is the number of distinct edge sizes, and n is the number of nodes. So rather than having node edge, having this non-backtracking matrix of size, node edge pair by node edge pair, we have this thing that's really just a scalar multiplied on the number of nodes. Okay, and the structure of this matrix, I'm not going to go into too much detail, but it's well understood. So it's Kronecker products, it's block structured using well-known matrices. A here collects adjacency information for each hyperedge size. D is a generalization of the node degree matrix. K is a list of possible edge sizes. And then we just have identity matrices involved. So these are very kind of clearly block structured, a block structured matrix that we can work with. Okay, and a real quick proof sketch in case you're interested. So the approach here is to show that our non-backtracking matrix can be written using 3 suitable operators, simpler operators S, T, and R as S times T minus R. These satisfy other really useful relations, like for example, T times S is equal to A, where A is that matrix that collected adjacency information for the different edge sizes. And then, of course, we're interested in eigenvalues. So we're going to look at the characteristic polynomial determinant of lambda I minus B. we're going to substitute in this rewritten formula for our non-backtracking operator and apply what's known as the push-through identity. So there's a kind of a well-studied identity that says that the determinant of a matrix combination like this, lambda I minus b, can be rewritten as determinant of x times the determinant of a simpler matrix using the inverse of this initial x. So simplifying, what we find out is that the determinant of this, or the characteristic polynomial of what we're interested in, the non-backtracking matrix, is related to the characteristic polynomial of this smaller matrix, B prime. It's just multiplied by a determinant corresponding to these uninformative eigenvalues. Okay, and feel free to interrupt me at any point with questions. So what do we get, right? This generalized Ihara-Bass theorem actually is incredibly powerful for computation. So if we had this previous example where we were going to be working on approximately 20,000 by 20,000 size matrices and doing eigen computations there, instead, if let's say k bar, the number of distinct edge sizes is just 3, then instead we're computing eigenvectors using about an 1800 by 1800 size matrix rather than 20,000 by 20,000. And you know, estimates for eigen computation say that we can probably do that about 100 to 1,000 times faster. So this decrease can be really, this decrease in the size of the underlying matrix can be really quite powerful. So our first algorithm says, let's compute this second eigenpair. We'll compute the second eigenvector associated to this smaller matrix representing condensed information from the non-backtracking operator. We'll separate the eigenvector into 2 pieces, and we'll take from the first piece all of the entries, aggregate them just by adding them up, and get some information about the cluster association, the cluster information for node I. So if this aggregated information from our eigenvector for node I is negative, we'll assign the node to cluster A, and otherwise we'll assign it to cluster B. Okay, so how does this work? Let me first introduce, we'll work with the same synthetic test bed throughout the talk. So what you're looking at in this plot is a bunch of different samples of these stochastic hypergraph block models where we have, as you move kind of up in the image, a higher density of 3 edges within clusters. So 3 edges are more likely to live within clusters as you move up. As you move down, they're more likely to live between clusters. And then as we move right through this image, we're more likely for 2 edges to live within clusters. So you can see over on the left side, the 2 edges are between clusters, more likely to be between clusters, and then within clusters over on the right. Okay, and so the eigenvector algorithm that I just presented to you is able to detect community, at least for many of these hypergraph block model, stochastic hypergraph block models. What we can see is that there's this kind of missing region. So we're able to do a lot when we're in the upper right, so lots of edges within cluster. We're actually able to do a lot also when the edges are between clusters, but when the edges of the different sizes sort of represent different information. So in these corners, we have 2 edges between and 3 edges within, or 2 edges within and 3 edges between. In either of those cases, this eigenvector algorithm struggles. Okay, so we're going to talk now about filling in these gaps. How can we Can we develop a better but similar spectral algorithm that's going to be able to fill in these corners that we might hope should be easy for detection? Okay, and the idea that comes to the rescue is belief propagation. So if you're coming from a different area, this is the cavity method in statistical physics. It's an approximate method for statistical inference. It's used in many different areas of statistical inference and machine learning. It's a discrete time dynamical system. Formally, here are the updates. I'm not going to go into detail here, but the idea here is that we're allowing nodes and hyperedges to communicate back and forth about the suspected cluster information of the nodes. So these hyperedges are using their information, their access to node membership belief, and the same for nodes, and they're communicating back and forth. And as these iterate, we might hope that they will iterate to convergence. They'll find a fixed point where they cease to iterate anymore. And hopefully that kind of fixed point that they end up finding will have good values, good understanding of the community structure for the nodes involved in the hypergraph. Okay, so that's belief propagation. And so I'm going to present one more, well, a couple more, but one more theoretical result. So if we consider a stochastic block model in which every node has the same expected number of attached edge, and the expected number of attached edge does not depend on the number of nodes, then the belief propagation algorithm has an approximate fixed point X bar that contains no cluster information, which maybe sounds a little bit unpromising. But more promising is that the Jacobian derivative of the belief propagation dynamics around that uninformative fixed point has kind of small valued entries except for this block J, which is going to be powerful for us to be able to calculate the community structure. And the reason is that when you're at this kind of uninformative fixed point, the unstable directions of the Jacobian derivative carry information about the community structure in the hypergraph. So we're going to be roughly speaking, the algorithm now is we're going to be wanting to use eigenvector information about this Jacobian derivative matrix, and really just this important part, J, in order to understand the community structure of our hypergraph. Okay, and once again, computation is a challenge. The matrix J, which is this kind of important part of the Jacobian derivative, can be a very large matrix. But similar to before, there's again a kind of understanding about the relationship between eigenvalues of this big matrix and eigenvalues of a much smaller matrix. I'll just mention the proof here is not quite as simple, so I'm not going to mention it, but I will describe I will talk a little bit about the result. So under mild conditions, again, if we have this interesting eigenvalue of the Jacobian derivative, then that value is also an eigenvalue of a much smaller matrix, J prime. And here it's 2 times the number of nodes times the number of distinct edge sizes times L. L here is the number of communities. And we can exactly write down this smaller matrix J prime using a couple of additional matrices. These other matrices K and I are all matrices we've seen for A and D. But G and G bar hold statistical parameters. They hold information from the belief propagation algorithm. Okay, so this is our new algorithm. We're using eigenvector calculations on this smaller matrix J prime. We were having issues from our kind of naive eigenvector based method in these kind of diagonal corners of our stochastic block model parameters. And when we work with this more complicated matrix J, or its kind of smaller friend J prime, we do increase the computation time over the naive algorithm from before, but it allows us to detect communities for more parameter combinations, right? And so you can see that we've really filled in these corners quite well. And the only places where we're having still a very hard time detecting communities is in this kind of round region in the center. Okay. So let me give you first a kind of example of the performance of this method on some real world data. So the data set I'm working with here comes from stack exchange tags. So the nodes in our graph correspond to specific tags that can be placed on stack exchange posts. So you can see some examples. You could tag that the post you're making is about Fibonacci numbers, it's about limits, it's about calculus. Here are a couple of examples of edges, right? The edges correspond to posts that share tags. So the derivative of a function at a vertical asymptote have to approach infinity. That post was tagged with calculus, infinity, and limits. So in our representation of this data, we consider a hyper edge over these three nodes, calculus, infinity, and limits. Okay, and what we see after running our eigenvector, hypergraph eigenvector method. So on the left here is a representation of the learned clusters, that's the colors here. And I'm projecting the data down onto just two components for representation, but really you should be focused on the colors. So the colors learned by the hypergraph community detection, or the clusters learned by the hypergraph community detection, place together these rationality testing, big list, right? All of these green tags, all of the blue tags, and these pink tags. And I'm going to highlight three of the pink tags: calculus, infinity, and limits. So our hypergraph method places these three nodes into the same community. Whereas when we run the non-backtracking eigenvector method on the projected graph. So we project the hypergraph down to a graph, form a non-backtracking matrix, and do clustering using that matrix. You can see that these three nodes of interest, calculus, infinity, and limits, end up in distinct clusters, distinct communities, right? And so infinity then is associated with, I don't know, Fibonacci numbers, rationality testing, online resources. So this is just a kind of a highlight that there are differences between these two methods. The hypergraph method, the hypergraph representation via the non-backtracking matrix, is distinctly different and allows us to learn some really coherent clusters on this stack exchange data. Okay, so finally, I'm just going to end with some brief comments on detectability thresholds, which really are alluding to some open questions, and then I'll wrap up. Okay, so recall our belief propagation based non-backtracking method for hypergraph detection has this kind of suspiciously round region where our algorithm totally fails to learn any cluster information, right? There's zero adjusted random rand index. And actually this region can be estimated. So the strategy is to ask when this Jacobian derivative matrix has an eigenvalue greater than 1. In that case, we have these kind of unstable directions with which contain community information, and otherwise we don't. We don't have information that we can gain about the community from that region, right? So we can kind of describe for different kind of parameter associations of our hypergraph stochastic block model. We can kind of I shouldn't say exactly, we can very well describe these regions where the community detection method fails. So I won't go deeply into this conjecture. Let me just say that the values that you're seeing here are depend upon the edge sizes and the number of edges of each size that each node is incident with. Okay, so once you have those are parameters just of your hypergraph information, we can write down these descriptions of these regions, and when we plot them, they're kind of remarkably aligned. And so to prove this result, we really need to utilize some random matrix theory to be able to say something with high probability rather than in expectation. In graphs, the failure of the non-backtracking spectral clustering coincides exactly with an information theoretic bound on the clustering problem itself. So what that means is that when that method fails, it turns out that no algorithm in those cases can actually reliably detect communities. And we conjecture the same thing for hypergraphs. So inside these ellipses, it's not just hard for our belief propagation, Jacobian, non-backtracking matrix to spectral method to fail. It's just actually that the detection in those regions are theoretically impossible. So a second conjecture. And let me briefly wrap up. So some future directions: prove the conjecture detectability threshold. So prove that these regions are truly exactly as described. And then additionally, a really wonderful contribution would be to show that this corresponds to some information theoretic threshold. In kind of a different mode, we'd like to go back to this idea of using tensor-based representations of the hypergraphs to develop community detection methods, but this will require some machinery development. And we'd also like to consider some other hypergraph block models with kind of additional and more complicated structure. And just to summarize the talk, so the non-backtracking operator enables us to use eigenvector techniques for community detection in hypergraphs, and importantly, in hypergraphs with varying edge sizes. We can develop determinant identities to help us speed up this eigenpair computation. And then finally, there are open questions around the fundamental limits of hypergraph community detection and its relationship to some of our proposed methods. I'll highlight again, this is work with these wonderful collaborators who are not just wonderful scientists, but wonderful people. And I will wrap up there. Thanks, everyone. And are there